Good afternoon, everyone. So what I'll be doing is, this is what I was just sorting through the slides as I was listening to the very interesting presentations, and I realized that though I thought that I have been able to trim down, but there might be too much information. So what I'm going to do is I'm going to go through the slides, sort of not necessarily going through everything that is in the slides. Hopefully that's not going to be too bad. So we are going to talk about our efforts in utilizing this growing area of what we call Internet of Medical Things, and the confluence of Internet of Medical Things and what we call hybrid analytics to deliver predictive and personalized virtual care. And I would acknowledge, I would like to acknowledge, let's see, our various partners, including Kaiser Permanente, UC San Diego Health, on the technology side, Teradata, Samsung, Qualcomm, and of course NSF. So there is a big trend going on in virtual care. One of the best examples of virtual care, though rare, is this hospital that I'm showing here, which is, I believe, in Missouri. And it's actually a brick and mortar hospital, but not a single patient comes into the hospital. It's really to deliver virtual care. It has all kinds of interesting instruments, a lot of AI databases and so on, but not a single patient that comes through. Our partners, for instance, Kaiser Permanente, has been delivering virtual care for some time, of course, through patient remote monitoring and video visits. Video visit is something that they have commercialized for quite some time. And also, interestingly, these mobile clinics and health vans. Mobile clinics is getting to be more and more popular, and health vans is something, I'm not sure how pervasive it is, but Kaiser is definitely pushing that quite a bit. So, and all this is possible because of the advances in wireless networks, computing, of course, and these medical devices and sensors and wearables, which are more and more wirelessly connected. We call them together Internet of Medical Things. And now, once you have the data that is collected by the Internet of Medical Things, there needs to be multimodal fusion, machine vision, and intelligence, and of course, computing and communication infrastructure to support what we call the next generation of predictive and personalized care. So that's what we are focusing on. While these commercial activities are going on, we are focused on how do we enable predictive and personalized virtual care. So as I mentioned that now so this is our goal. It's not like we are successful already, but this is our goal to enable personalized recommendations and interventions using this virtual care analytics. And so there's one project I'll quickly go through. In this project, we are continuously collecting for users both stationary conditions like your home, office, maybe hospital, as well as when you're mobile, in your vehicle, maybe assisted vehicle, autonomous vehicle, in a train. In any situation you are in, we want to continue to collect data and analyze the data. And the kind of data that we are collecting is, you can classify it as threefold. One is behavioral data, exercise, sleep, diet, and so on. Vital data, various kinds of vital data that is possible today, but many of our faculty, as sure in this campus, are coming up with new kinds of sensors which are going to sense and report on other kinds of biometrics. But today we are using FDA-approved sensors and wearables, collecting BP, pulse oxidation, body composition, and so on. And then contextual data, which we have found to be quite important, your demographics, location, environment, and so on. And using this data, we would like to do two things. We would like to create these prediction models for your target variables. So this data will be your feature set, your attributes, and then there'll be target variables, like in this case, it can be BP, your blood pressure level, your A1C level. But we also would like to figure out how these features correlate with each other as well as with the target variables, and what is the importance of the features. So this is also what we want to develop. Now, to give you a quick sort of glimpse of some preliminary results that we have and models, essentially what you see, what we are presenting here are data from 2 users. On the left-hand side, user 1, right-hand side, user 2. And what we show here, so imagine that we have already developed the predictive model for blood pressure. And we are giving that blood pressure model some values of the attributes. For the same values, for the 2 users, the models are giving very different predictions. And this is to be expected, right? We all know that what affects your blood pressure is different than what affects my blood pressure. And yet, when my body was flirting with pre-hypertension or hypertension, my doctor gave me a list of things to do. All these kind of things which increases my potassium level, all these other things which reduces my this level and that level. I was a good student, and I tried to be a good patient, and I tried to follow everything for a month, maybe 2, but then I started giving up. There were too many recommendations, too generic. And so actually this had motivated me, because I was collecting a lot of data for myself. And this started motivating me to play with the various things. Maybe I don't do exercise today. Maybe I take less bananas today. So I tried to started playing with all these different recommendations, but I couldn't figure out completely what affects me. And the great thing is that what we are seeing through our data and through the analytics models is that we are, I think, reaching that point where we are able to tell you precisely what exactly, how exactly these features are going to affect you. And even more importantly, if you look at the left-hand side and the right-hand side, what you see for user 1, what we are showing in red are the 2 top features that are affecting user 1, and same on the right-hand side. And what you see are that there are 2 different kinds of features which are affecting or which are most influential in the blood pressure level of user 1 versus the blood pressure level of user 2. So what you are seeing is what we are trying to do is pinpoint what are the important features that affect you, your blood pressure versus someone else's blood pressure, and then based on that, hopefully your caregiver can give you more personalized recommendation, and hopefully you'll be able to follow those recommendations more and not get lost in the sea of things that you need to do, like I got lost. So a quick snapshot of correlation, this correlation heat map I'm showing, all the features on the left-hand side, and the column as well as the row. And what you see the correlations, and I'm not going to go into details of this, what you see these correlation heat maps, red is when 2 features are very positively correlated, and blue is when they are negatively correlated. And what you see is that these heat maps for different individuals look different, okay? Now, why can we not use the correlation heat maps? Because they don't, when the relationships are nonlinear, they're not very useful. So we have to find out other techniques of how to identify these correlations, how to identify this, what we call feature importance. I'm sorry, I'm going to skip through this. So we played with various different machine learning techniques, deep learning techniques, and at this time we have settled on this technique. Many of you and most of you, I think, know of random forest, random tree. This is a random decision tree. This decision tree, we start with all the samples. So these are the training samples. So in the training sample, in our case, there are all the features, calories burned, likely active minutes, number of awakenings, and all those things, and the target variable, which is a BP. And the first node, you figure out the estimated blood pressure by finding out the MSE of all the samples that are in that first node. Then you have decision. So each of the variable you use as your decision node. So for instance, we can use minutes of sleep. If your minutes of sleep is greater than 400, then the samples go on the left-hand side. If it is less than 400, it goes to the right-hand side. So you essentially using these variables, you're partitioning your sample set. And then when an actual live data comes, so a new sample comes, then according to the values of the new sample and the decision tree, you keep getting to the leaf node. And your estimated blood pressure is the average MSE of the samples in the leaf node. So that's how the decision tree works, not our invention. And the decision nodes have this interesting thing that they keep reducing the MSEs. So if you look at the initial MSE, it is 300, and the mean square error after you apply the minutes of sleep reduces. So as you keep applying these decision nodes, you keep reducing the MSE. And the feature importance of a decision tree is essentially the reduction in MSE, and whichever variable reduces the MSE by most, we call that the most important feature. Now obviously a question going through your mind is, if you have one decision tree and you're randomly deciding on the variables, then whichever variable you're picking first will be the variable which reduces MSE the most, right? So it's really flawed. But to overcome that, what we do is we create this random forest. A random forest is nothing but you're taking subsets of the sample set, the training set, as well as subset of the features, and creating decision trees randomly. And so you create hundreds and hundreds of decision trees, and then you average the value, the BP prediction, as well as the feature importance from all these decision trees. Okay. Now the problem though is that if you notice that all of the data we are collecting, your sleep data, your diet, your activities data, all these data are time series data, right? Whereas the decision tree treats, or the random forest treats each sample as an independent event. So we need to address this, because otherwise there is too much error. So the way we do it in this particular use case is we resort to feature engineering by adding features which give a flavor of the historical BP values. And so for instance, we add a feature exponentially weighted moving average. We add other features which tag days and morning and so on, essentially temporal data to your training set. And but even then, because now you're adding a lot of features, it increases the dimensionality of your data set. It tremendously explodes how many features you have. And that creates another problem, and that is overfitting of data. So those of you in machine learning know that that again becomes a big problem. So what we do is we select features based on feature importance. Now the question is, if you're selecting some features and not all features, how are you sure that you're selecting the most important features? Or your most importance, the importance levels are correct. So what we have seen is that we could have created one random forest with thousands and thousands of trees, okay, to make it as stable as possible. But that is very time consuming. The training time is very, very large. So what we do is we create multiple forests, each with smaller number of trees. And so with the data, and after pre-processing of the data, we have multiple such forests created, and then we average the data across the forest and create our primary RF model. So that's the technique we do. And to give you some results, so we do a five-fold cross-validation, randomly splitting the data into training set and test sets. And what we see is that the model, the approach we are proposing, RFFS, is consistently doing better. RFTS, which is when we add these temporal features, can be very good. So using the historical data can be good for some users or some patients, and cannot be good for some other patients. Okay, so there's an inconsistency there. Whereas our model, where we also add, not only we add the new features, but we are doing the feature selection, stabilizes and has much less error, as you see here. It gives about pretty high accuracy, about 5.18 and 4.30 in systolic and diastolic in absolute errors, and 4.31% and 5.64% in terms of MAPE. And it outperforms the other models fairly significantly. Now, one of the things as I listen to the morning sessions, and this is something that obviously we have been questioning ourselves for quite some time, is that as we are collecting data for various individuals, why not aggregate all the data and create one aggregated model, one generic model, right? That's the kind of conventional thing that we have done in healthcare. But as you see here, that the conventional approach of creating a generalized model actually has much more error, about 23% to 14%, depending on which kind of blood pressure you're measuring, than a personalized model. So a personalized model is using much less data set, right? And a aggregated model is using much more data set, and yet the personalized model is much more accurate. And that is what we expected, but using data we are showing this. And now the challenge though is that, so when a new user, for instance, joins, let's say there's a service, a new user joins, you don't have his data, right? So how will you create his personalized model? So one of the approaches we are trying, very preliminary stage, is using clustering technique and using transfer learning. So essentially, can we divide up the user set into multiple clusters with similar characteristics, and then when a new user comes, you are essentially using data from that set and also using transfer learning techniques. We are just, we are also learning what to do here. We don't have any results. The other thing is, again, when a new user comes in, as you use transfer learning and come up with a little more personalized model than the generic model that is stored in the cloud, can you also use online learning techniques to learn as the user is starting to use this model and as data is being collected, but not taking 6 months and 1 year as our, the results that I was showing. Now, what is the effect of all this? Remember, I mentioned that our goal is personalized recommendations. Our goal is personalized interventions. So this again some experimental data, very preliminary, not to make huge conclusions from yet. So what we did was we asked some of the users, not all, who were volunteers in our study, saying that we will provide you your top 3 features, that is the features that most importantly affect your blood pressure level. And we are not going to tell you how exactly to effectuate those features, but common sense has it that you increase your exercise, or you change your sleeping habits or change your diet habits. So for instance, this particular user 1 here, anonymous, we told him or her that these are your top features, and what they did is in this particular case, this person did more activities, and so ended up burning more calories because, and so address these top features by doing more exercise essentially. And in this case, for this user, we told that user different features because those are the features that are most important for that user. And again, they change their lifestyle to effectuate their top features. And what we see is that, and we do 2 weeks of data collection again, 1 week when they did not change their behavior, another week when they changed their behavior. And we see that and this is a day-to-day effect, and we see on the average, their blood pressure levels did go down when they followed those personalized recommendations and tried to change their behaviors essentially. For the second user, and I wanted to show 2 because in this case, this was much more effective. In this case, it was effective. So it went down from 106 to 102, diastolic went down from 68 to 63, but not as much as the user 1. Okay, so there's still much for us to learn, understand, what those recommendations should be, how they should be effectuated. Now, there's just when Somali was telling me, and I was discussing with her how I should present because what Somali and others have done is put together a very diverse set of speakers and audience, different kinds of interest and so on. So one of the things I acknowledge is that one of the things we need to do much better or need to get into more is what do we do with the data, how do we collect the data, how do we store the data and so on, and I'll talk a little bit about it more. But I was thinking that from a database community, what are the things that we can talk about improving, right? I mean, what are the lessons learned and what we can do? One of the things is in data collection itself. I think that one of the speakers or panelists had alluded to it before maybe, but the medical sensor data can be very, it's still error prone. So, you have to do other kinds of safeguards to make sure that this data, either you throw away a lot of data, which seems to be erroneous, or use the data in a different way, sort of maybe a stepwise machine learning model. One of the things that we are looking at is how to automate all the data collection and enable streaming of data. Because whenever you are relying on users to add data, let's say the nutrition data, we don't have streaming data at this time. So people have to enter their data, and that can be very erroneous. So that's what we are working with multiple different partners, including Fitbit, including Samsung, and so on, that how do we automate the data collection and the always on streaming paradigm that we are trying to push. We want to expand what are the other kinds of data we can collect. We are collecting some data, and we want to expand collection of other data, and we are constantly working with in faculty to try their experimental sensors in this setup that we have. And so anyone who are developing sensors here, we would love to work with you to put it into our study. One of the things that we have been also toying with, so through data, without knowing more about how your genomes are or your exomes are, what we are trying to figure out is your personal traits, right? What affects you versus what affects someone else. But maybe there'll be even more utility if we add to it the various kinds of exome data, microbiome data, and so on. That will be an interesting confluence that we would love to study. We want to develop predictive models like we have done for blood pressure, for the other chronic diseases like diabetes. And that's one of the projects that we are just launching this summer. And develop transfer and online learning techniques, as I had already mentioned. And as you saw that, to validate the importance of the features, we did some experiments, right? But instead of doing these experiments, can we come up with measuring techniques which can measure in more analytical ways what are the effects of these personalized recommendations, and also how to come up with the personalized recommendations and personalized interventions. And finally, for this project, we would like to address various practical issues: privacy, the security of the data, the delivery cost. Imagine that all this data, because remember we are making this data collection mobile wherever you are, right? So all this data going to the cloud obviously is a privacy concern, but also it's a lot of cost. So we want to partition, and we have just started working on it, partition the data collection and the data analytics between the edge nodes, which might be an edge hub, or it might be your mobile device, and that's why we are working with Samsung. So how much of the analytics work should be done in the edge versus how much of it should be done in the cloud is an open question. On one extreme, everything is done on the edge, and only your performance data goes to the cloud. That means how you're doing in terms of your recommendations goes to the cloud. On the other extreme, everything goes to the cloud, and the cloud does everything, right? So we are creating this platform where we can study the trade-offs. Very interesting questions come up in data storage, databases itself. For instance, how much data to store, where to store, what kind of database we should use when a lot of data is data that you want to own versus give it to your healthcare provider. Should the database be, it has to span your mobile devices. So the database here is not just your big cloud. The database spans into your mobile devices. So how do you architect that? And one thing I also would like to mention, if you look at the cloud has to do collective learning. because each of the edge devices is creating its own personalized model, keeping on learning and so on. That's great. But there's obviously wisdom in understanding from a collective sense how everyone is doing, right? So that is what we are doing on the cloud. That is the effect of your recommendations that is going to the cloud, and the cloud is learning from it, and the cloud is doing this kind of collective analytics. But another model we are toying with is, can we do this kind of collective learning using a more peer-to-peer paradigm? That is, each of the devices is sharing with each other in a more secured way, maybe using blockchain, to do learning on the fly, as opposed to involve the cloud. So those of you who might be following, there's a lot of impetus today on edge-based computing as opposed to the central cloud-based computing. And so we are following that. We have been working actively in that, and this translates to this project also. And finally, using a lot of new network paradigms that are coming up. So network function virtualization, software-defined network. We would like to have a scalable architecture with service-based flexibility of this analytics partitioning, because Kaiser might want a different kind of partitioning between edge and cloud. Maybe Sharp Medical might want something else. Stanford Medicine might want something else, and so on, right? So we hope to create this kind of scalable architecture using this using these network virtualization techniques. I had, if you may allow, I just wanted to show just one slide and not a lot of slides. As I had mentioned that, I realized that I have a lot more slides. And I did follow the discussions we had before the conference, but I just wanted to show this one thing, and that is, the collection of data and use of data is permeating various different areas in what we are collectively calling connected health. And I just wanted to show this because machine learning and deep learning is becoming very, very important in training in various aspects of medical science. And in this particular case, we are building a system with UC San Diego Health where it's being useful in training patients, follow up on their physical therapy training in the clinics. So in this system, what we are doing is, instead of you going back from a physical therapy session with a sheet of paper and you are practicing with a sheet of paper, what we are doing is we are modeling the session in the clinic, and then we are creating an avatar of the physical therapist. And that avatar is sitting in the cloud, and when you are at home, in your hotel, you are following the avatar, and the avatar is also following you because of the sensors you are wearing. So motion sensors, pressure sensors, and so on. And then using those sensors, the avatar is trying to understand how you are performing vis-a-vis the instructions it's giving. And this we are developing on various platforms, using a tablet, using a VR device, using AR, where the guidance is coming on your feet or on your arms. So what is happening is that based on how you're performing, the avatar is sending feedback to you. How the feedback should be given, in what form should be given, all depends upon different users and the different intervention techniques. And then based on this feedback, and when you start doing well, then the question is, how do you move to your next task? How do you move to the next level of therapy? And so for that, we are studying Parkinson's patients using, with the help of our colleagues. And we have developed essentially a model which can mimic a physical therapist in the clinic, and so that the users of this system can avail of it even from remote locations. They don't have to come back to the clinic every time. They can be monitored, and they can be, the next levels of tasks can be provided to them with the supervision of the physical therapist. So that is also a very exciting project we are doing, and getting to a stage where it hopefully will be implemented sometime very soon in UC San Diego Health. Thank you.
Questions? I had one question, which is that within, I I guess you're talking about personalizing, but at the same time moving computing out to the edge. You would think that in a given household, there's much more likely to be a confluence of environmental factors, perhaps nutritional factors, and of course genetic factors if the people in the household are related. So does that mean you can simplify things by developing models for everybody within a given sort of network node?
Right, so what you just gave a big hint is how clustering should be done. Remember I said that there's this trade-off between each onto, for himself or herself versus learning from others and clustering. And so clearly what you just mentioned is that there should be, the family members, clustering of the family members should be good. On the other hand, as we know that, yes, so genetics can be captured in that sense, right? So our goal is to create, I still don't know what term to use, but kind of a personal guide, which will be monitoring everything for you and give you recommendations. How we give recommendations without coming across as nagging is something that we are working with our cognitive science faculty. But clearly there is a value of data aggregation and learning from others. And so the family aspect that you said is, maybe one way of doing it. But there'll be more generic ways of doing things.
Okay, thank you very much.